Welcome back to Module 2 in our series on building decarbonization. Engineers, designers, and contractors are particularly critical to building decarbonization because they touch so many phases of the design and construction building lifecycle. From sourcing materials to design, pre-construction, construction, and maintenance, and communicating with owners and subcontractors, making them a conduit for change. Hello, I'm Kent Peterson, and I will narrate this module. This presentation series is presented in 4 modules. Our previous module provided an overview of decarbonization and applicable terminology. This module focuses on understanding global decarbonization issues, electric grid impacts, and provides an introduction to embodied carbon. The future 2 modules will focus on ASHRAE involvement in building decarbonization and discuss a pathway to building decarbonization. Let's begin with why building decarbonization is an issue from a global perspective. The building sector is a significant source of global carbon emissions. According to the International Energy Agency, building energy accounted for 37% of global energy-related carbon dioxide emissions in 2021. Residential buildings accounted for 17% of energy-related emissions, while non-residential buildings accounted for 11%. Direct energy-related emissions from buildings comprised 38% of the building sector, while indirect emissions were 62%. HVAC systems account for roughly 15% of total energy-related carbon dioxide emissions. Building construction was substantial at 24% of building sector energy-related emissions, since the building sector typically only adds 2% annually to the global building stock. Building refrigerants, not included in this figure, provides additional carbon emissions. Studies from several U.S. states show this to be roughly 10 to 12% of total annual building-related greenhouse gas emissions. Remember that in 2021, indirect emissions from buildings accounted for roughly 2/3 of total global building energy-related operational emissions. Most of those indirect emissions came from electricity generation. Low-carbon electricity sources are going to be essential to reduce indirect greenhouse gas emissions from the building sector. Low-carbon electricity can come from nuclear or renewables such as hydropower, solar, wind, and geothermal. The contribution of each varies from country to country. Globally, 39% of our electricity came from low-carbon sources in 2020. But there's a lot of variation in the low-carbon electricity production worldwide. World electricity generation has added roughly 3,700 terawatts of low-carbon electricity generation since 2010, increasing it by 54% in the past 11 years. China has accounted for roughly half of that global low-carbon electricity generation growth. We will need to figure out how to substantially reduce emissions from the world's reliance on electricity generation from coal. As we look for solutions, it's important to understand why we've relied on coal in the past. Coal has been a reliable and affordable energy source. It's abundant, and it's easy to extract and relatively inexpensive to transport. Additionally, it is a very efficient fuel source, meaning that a large amount of energy can be produced from a small amount of coal. As we look to reduce greenhouse gas emissions, coal generation produces more than double the greenhouse gas emissions when compared to combined cycle natural gas generation. World electricity generation added roughly 1,700 terawatts of coal electricity since 2010. Many countries have decreased their coal generation during this period. China's growing economy added roughly 2,100 terawatts of coal generation since 2010. Slightly more than the amount of low-carbon generation they added during the same time frame. Carbon intensity on this chart is shown in grams of carbon dioxide equivalents emitted per kilowatt hour of electricity generated. The electric grid carbon intensity has been trending downward since 2010 in many parts of the world. Much of the reduction is due to the rapid increase of low-carbon generation and natural gas generation replacing coal generation. Economics will continue to play a critical role in the overall solution sets as we transition towards low carbon generation. The energy around the globe must be accessible and affordable. The greenhouse gas carbon intensity from an 80% efficient natural gas boiler is shown. The boiler's actual annual operating efficiency is closer to 70% when accounting for off-standard stack losses. The electric grid carbon intensity values typically increase by 5% to account for the electrical distribution system losses to the building. This is why efficient electrification of heat loads will be required using heat pump technology. A heat pump with an operational coefficient of performance of 2.0 or 200% efficiency would cut the electricity carbon intensity in half per kilowatt hour of heating. Electric resistance technology would generate more emissions than natural gas boilers in many areas of the world. We have been reviewing the global and country electricity carbon intensity trends. We will now explore this inside a country. This slide uses the United States as an example. These electric grid carbon emission factors vary substantially across the various subregions in each country. In 2020, the average United States electricity emission factor was roughly 371 grams of CO2 equivalent per kilowatt hour. But the subregions vary from 106 to 750 grams of CO2 equivalent per kilowatt hour. This range is 7 to 1. Locations and generation sources can vary substantially for electricity grid carbon emissions.
Building electrical demand flexibility is becoming important as the grid gets more renewable generation. And I'll use California as an example, since it's quickly moving towards solar and wind generation. In 2020, roughly 30% of the electricity came from renewable energy sources. California forecasts 60% renewables by 2030 and 100% by 2045. Since solar and wind generation sources are considered non-dispatchable, the grid carbon intensity will have substantial deviations depending on the time of use, as shown in this figure. The dark green is representing low carbon electricity, whereas dark red could produce 4 times the carbon emissions when compared to the low carbon periods. For electrification to fully realize its carbon reduction potential, buildings need integrated sequences to coordinate supply and demand and shift energy use using thermal storage systems. Let's now explore what may be required to achieve building decarbonization and net zero energy-related emissions by 2050 from a global perspective. The International Energy Agency Net Zero Emissions by 2050 scenario shows a global roadmap to get to ZNE by 2050. This chart shows what will be required to reduce direct emissions from buildings. Direct covers emissions from fossil fuel used at the building. You can see the substantial potential increase in direct emissions from new global building construction in the next 30 years. Most of this will occur in the global south. What is important is that 30% of the direct emissions must be reduced with energy efficiency before electrification. Electrification is expected to account for another 40% reduction. The loading order makes a difference in not overloading the electric grids and helps provide better life cycle costs when electrifying these loads. Efficiency measures in building heating systems can help lower demand for carbon-intensive energy in the near term and can make it easier to ultimately reach net zero emissions. This chart shows what will be required to reduce electricity usage from buildings. The previous slide showed direct energy, while this is indirect energy. Again, we see a substantial potential increase, double today's electricity consumption, from new construction and the electrification of direct energy building loads in the next 30 years. Roughly 40% of electricity consumption in the building sector needs to be reduced with energy efficiency. The takeaway from the previous two slides is a substantial portion of global building sector operational energy carbon emissions reduction will need to come from energy efficiency. What is more elegant than energy efficiency? A kilowatt hour saved is the cleanest and greenest. This is a win-win since it addresses both direct and indirect emissions and improves the economic viability of the investment. The good news is many parts of these elegant solution sets for energy efficiency exist today. Energy efficient building envelopes, passive design strategies, heat recovery, heat pump technologies, energy storage, and efficient control strategies, to name a few. Lately, there's been a lot of discussion around whole life carbon emissions based on the life cycle of a building. As discussed in Module 1, whole life carbon emissions include embodied and operational carbon. As we can see from the left side of this figure, building greenhouse gas emissions are locked in place as soon as a building is built, even before its operation. This starts with the extract, transport to the factory, and manufacture during the product stage, to the construction stage, transporting to the site, and constructing the building. We have both embodied and operational emissions during the maintain and use stage. The operational carbon is energy and water related emissions during the use of the building. Equipment replacements and the building renewals add additional embodied carbon during this stage. It doesn't stop there. We also have embodied emissions at the end of life stage due to demolishing the building, hauling away the waste materials, and whether we send it to a landfill or recycle. The last stage is beyond the life cycle that covers the emissions for reuse and recovery. Reducing both embodied and operational carbon in buildings is critical to achieving a more sustainable and low carbon future. Governments and other organizations are beginning to understand the importance of evaluating means to reduce embodied and operational emissions. Let's further explore embodied and operational carbon emissions over the first 30 years in the life of a building. This figure shows the embodied carbon impact of constructing an all-electric commercial building with cumulative energy-related carbon emissions. The Carbon Leadership Forum's embodied carbon benchmark study, with an average of 400 kilograms of CO2 equivalent per square meter, was used to estimate the initial embodied carbon through construction. It is also assumed that an additional 100 kilograms of CO2 equivalent per square meter is used at year 15 for building renewal during the use stage. The 2020 U.S. electric grid average emission rate of 371 grams per kilowatt hour was used as the initial grid emission rate. Linear regression was used with the annual lowering of the electric grid emissions. This assumes the grid achieves 90% decarbonization in 30 years. The first scenario shows operational carbon for an EUI of 30 kBTUs per square foot per year, and that's equivalent of 95 kilowatt hours per square meter per year. Embodied carbon accounts for roughly half of the total carbon emissions in the first 30 years of operation. The takeaway is embodied carbon can be significant. Scenario 2 improves operational carbon with an EUI of 20 kBTUs per square foot per year, or 63 kilowatt hours per square meter per year. Since there are no cost and low-cost ways of reducing embodied carbon by at least 25%, we've assumed the initial embodied carbon has been reduced to 300 kilograms of CO2 equivalent per square meter. Scenario 2 achieves a 30% carbon emission reduction compared to Scenario 1 in 30 years. If only operational carbon were addressed, then that reduction would drop from 30% to 18%. The takeaway is that the building industry is moving towards considering whole life carbon impacts. The key takeaways from this module include: the building sector significantly impacts global greenhouse gas emissions from embodied, operational energy, and refrigerant emissions. As we look to electrification as an alternative to decarbonizing buildings, the electric grid carbon intensity will need to move towards net zero emissions by 2050 to recognize the true benefits. We also discussed that carbon intensity could vary by time of day, and buildings can be designed to interact better with the grid to minimize overall emissions. Energy efficiency is the #1 strategy to reduce greenhouse gas emissions. The building industry should consider the whole life carbon impacts and not only focus on operational carbon emissions. And finally, embodied carbon does matter in both new and retrofit projects. This concludes the second module. Please join us for the third module to explore ASHRAE's current plans to help decarbonize the building sector.